computer. Okay. All right. So this is what I think would be better in the sense that it would have more interaction. Everybody can interact a little bit. So I will share my screen with you, and that would be my iPad screen. All right, let's wait a little bit. Let's see. Okay, so that is good. It should be fine. Okay. Can you see? You can see my you can see my screen now, right? What is? Okay. Section.
Yeah, I can see it fine.
Okay, very good. So this is what I'm going to do. We are going to do it live, and then I already upload the lectures for 3.3 to the Canvas side. In the future, I would upload it a few more days before the class, and then you should go ahead and look at the study the lecture notes before the class. Then I will go over the lecture notes during the class. So first of all, I want you to so all of you, if you cannot see clearly what is on the share screen now from my my iPad, let me know now, so I can see whether I have to switch to other. The handwriting probably is not dark enough, but I hope you can. All right. So we are going to talk about section 3.3 today. But before we talk about it, we actually would kind of go back to review what we have been talking about in let me see what is the best way. Yeah, it doesn't matter anyway. All right. So the so last time we talked about this function space L2 AB. So this is a space of functions on AB, so that you take the square and you integrate from A and B, from A to B, and this the integral would be finite. So this is usually requires the L2 space. On this space, we define an inner product. The inner product is defined in this way. So this you modify these two functions, and you integrate from A to B. So that would give you a number. So that this inner product would satisfy the axioms. And then, so once you have an inner product, then you can define the concept of angles. Then, and you can also define the concept of norms. The norm is defined, the square of the norm is defined as the inner product of the function with itself. And the angle is defined, so let's say the angle between these two functions, AB, is defined as the cosine of the angle is the inner product of F and G. If you go back to look at your linear algebra, if you take your linear algebra over the norm of F times the norm of G. So therefore, F is perpendicular to G. That means that this angle is pi half. That would mean that the numerator here, cosine pi half is 0. So that would mean that the numerator here is 0. So that is, this is perpendicular if and only if the inner product of F and G is 0. So far so good. Anybody? Tom, is it you follow what I'm doing now? Tom? So when I ask you a question, you can unmute your microphone and you can respond. Okay. Melissa, you follow what I'm talking about so far?
Yeah.
Yes, I follow.
Okay, very good, very good. All right. So last time we talked about these generalized Fourier series. If we have a function, a sequence of function Fn, we call it as an orthogonal system. Just means that each of F, J, and is orthogonal to Fk. If J is not K, their inner product is 0. Then, if a function is written as an infinite series of involving this system, so you have these an are coefficients, are constant, are scalars, then now when we write this way, when we have infinite series, then these coefficients are given by these formulas. These are the formulas that give you the coefficients. Sydney, do you know when we have infinite series, then it would be, you need to think about conversion. What kind of conversion are we talking about here, Sydney?
Point-wise, or?
Actually, it's not in this case. It's not point-wise. Is the L2 the mean square conversion is with this norm in this theorem. This conversion here is a mean square. Mean square conversion. So therefore, one need to be careful about this convergence of an infinite series. Sometimes I would explicitly saying that, but sometimes you can see from context. But in this case, it's convergent in this mean square. So that means that the norm of this, you have a finite sum of these f(x) and f(x). This converges to 0 in norm, in the L2 norm. So that is the convergence. Now then, if f can be written in this way, then we have these Bezo's inequality. So that is, this is the Bezo's inequality. And Now we also give a definition. We say the sequence, this sequence of function, this system, this orthonormal system, orthogonal system is complete orthogonal. That would mean that in this case, instead of having an inequality, we have an equality. So that is the Parseval's equality. So that these are the materials that we talked about last time. Any question? Okay. Now, but these are the general theory. However, for the classical Fourier series, we actually these functions fn are going to be the trigonometry functions, are going to be sines and cosines functions. So last time we also talked about Fourier sines function. The Fourier sines function, this is fn. In this case, the orthogonal system is fnx equals to sin nx. And n runs from 1 to infinity. Now, in this actually, this actually is going to be, and this is on the interval from 0 to pi. And this one can prove, and we are not going to prove it here, this is a complete orthogonal system. So you can write fx, any function fx can be written in this way, and this convergence at this point is mean square convergence. Okay. Convergent in mean square norm. Now, last time we also proved that this actually is indeed an orthogonal system. Orthogonal system means that their inner product is 0, and when n is not m, so that is an orthogonal system. And we can also calculate this integral when n is m. Marisa, do you remember how did we evaluate this integral here? Can you hear me, Marisa? Oh, so it looks like some student drop off, is that right? Maybe I can also have this audio on in the. Do
you mean the calculation for a of n?
Yeah. How do you evaluate this integral?
I'm hearing like a really bad echo.
Oh, okay. So it looks like I have to turn off canvas in order for the sound to be good. So is the sound better now?
Yes.
Okay, so it looks like we cannot turn on both of them at the same time. All right, that's fine. Okay, now, so how would you evaluate this integral here?
We did the sine of nx dx equals negative cosine nx over n.
Yeah. So we actually use this formula, sin A sin B equals to 1/2 of cosine. This is A minus B minus cosine A plus B, or some formula in a slightly different form, and then we compute this, and then that is how we prove this. When n is m, then this will become psi n square, and then we use this formula psi n square A equals to 1/2 of 1 minus cosine 2A to evaluate the integral. Okay. All right, so then Bn is compute. We can calculate Bn with this formula, and in this case, the Parseval's equality is in this form. So originally we have the norm of Fn square here, but the norm of Fn square is pi 2, and then we divide it both side by pi 2. That is how we get this 2 over pi. How we get this 2 over pi identity. Is that clear? Albert, are you following what I'm talking about here, Albert?
Yes, I believe so, Professor.
What did you say? Okay, so that's fine. So, yeah, I'm trying to figure out what is the best way for this remote instruction. But let me try at least for today this way. Now, so for an orthogonal system, if we choose Fn equals to sine nx, it is Fourier sine series. But we can also choose another system, that is then we choose 1 cosine x, cosine 2x, and cosine nx. This actually will give us a Fourier cosine series on this interval from 0 to pi. Now, then again, we can prove that this is orthogonal, and then you have this inequality, you have these identities, and therefore this again is a complete orthogonal system on 0 pi. So whether a system is orthogonal or not, and it depends on which interval you are talking about. So it's always, you need to identify your interval. When we say this is an orthogonal system here, we also means that it is on 0 pi. Okay. Any other questions?
Just a quick question. Just trying to read. For the most part, it's very clear, not nearly as pixelated as it would be with Big Blue Button. So I'm so far appreciating the platform Zoom. But right here under example 1, where the line starts fx equals the sum from n to right. The very next, within that sum, we have B subscript. What is the subscript? Is that an N?
Subscript 1, B1, and then the next subscript is B2, B1
Okay.
here, B2.
Just to on the other side of the equality, that's a B subscript of what?
Subscript 1. So this is B1.
Okay. And then, sorry, just on the left side of that equality sign, so that when we have n equals
this
to infinity.
This should be Bn. Bn.
Okay, great.
Yeah.
All right, thank you.
Yeah.
Appreciate it.
Any other questions? All right, if no question, again, feel free to jump in and ask me question as I go on these lecture notes. So these so when we write the express a function fx in terms of a Fourier, this is a Fourier cosine series, then the first constant is this is like a0 over 2 is the same as a0 over 2 times 1. So the 1 is the first term here, and then all the other. But here we choose a0 over 2 because in the next slide you would that the formula for an will be consistent with each other. An and a0 all using the same formula. Again, to evaluate this integral, we use a formula that is similar to what we have here. But in this case, we have cosine A cosine B equals to 1/2. The same thing, but this is plus sign. So you have cosine A minus B plus cosine A plus B. So this is the formula that we use to evaluate this integral. This formula to evaluate this integral. Now, the ANs are given by this formula. So very similar to what we have for the Fourier sine series. The only difference here is you replace the sines by cosine. For the Fourier sine series, this is times sine, but Fourier cosine, this is cosine. And the Pascal's equality for this the same reason is this one. I would recommend you after this lecture, if you haven't read it about these lecture notes before trying to read the lecture notes, I will post these lecture notes with annotated that I have remarks right down here on the Canvas side as well. Any question before I proceed?
One question, where will you be uploading the videos, the recordings for our Zoom lectures?
Oh, it's the same under module. You look at a Canvas module, right?
Okay, gotcha. Thank you.
If my recording is successful, okay, then
right.
I will upload it there. So in the next example 3, now we so far we have only we have the Fourier sines and the Fourier cosine, but we can also combine sines and cosine together, and we have full Fourier series on. But notice the interval here is from negative pi to pi. This is from negative pi to pi. Now the function is also the combination of the functions the systems that we had before is, but you have one cosine, but you also have sine. We have both cosine and sine. So this is what we call as a full Fourier series. It has both sine and cosine. Now this again is complete orthogonal system. But let me emphasize that it is this orthogonal system is on from negative pi to pi. Not in our previous tool, it is from 0 to pi, but here it's from negative pi to pi. And you can double check that these integrals. Please to go back and double check this. This integration using the trig identities I just mentioned. And then actually there's also another one. This cosine and sine is always orthogonal. Even n and m are the same. They still, this integral will give you 0. But for cosine, and cosine, if m and n are the same, then the integral is pi, but m and n, if not the same, it is 0. And for sine, it's the same thing. If m and m are the same, it is pi, and m and n are not the same, and its integral is 0. So I go back and use these trig identities. What is a cosine A sine B? What formula did we use? Sydney, do you remember this formula for the trig identity that we use to evaluate this integral here?
No, I don't remember it off the top of my head.
Okay, so it is sine, no problem, is sine A. Let me see, A minus B, okay, A plus B minus sine A minus B. Okay, so this is the trig identity. You can go back to double check, use the sum and difference formula for sine and cosine to double check this formula that we have here. Now, any function that is an L2 function from negative pi to pi can be expressed in this full Fourier series. And again, the convergence is in mean square norm. And then the AN here is given by this formula, and BN is given by this formula. And then the Pascal's equality is this formula. I guess in the future I will keep enough space for this writing so that you can see it more clearly. And I guess I need to use a darker pen to write this so that when I scan it is it's better.
Quick question
Yeah.
about one of your earlier notations, or annotations. So at the top of 48, I believe, you wrote that the cosine n of x, pointing to it sine n of x. What did you mean by that?
Oh, I mean that this formula is the same as the sine series, except that here is cosine. For sine series, this
Oh, okay, gotcha.
For sine series, it is this. Okay, that is what I meant.
Okay, thank you.
All right. All right. Any other questions? So you may wonder by now, why do we have all those? We have sine, and then we have cosine, and then we have a full Fourier series. What are the connections for these? The point is that actually all of those are consistent with each other. If you examine it more carefully, that is what this remark is about. Now, let's look at the Fourier sine series. Now, if you have a function, the Fourier sine series is for a function from 0 to pi. If I have a function from 0 to pi, like this function here, okay? Now, I can extend this function to from negative pi to 0, and it is as an odd function. I may not draw it exactly as an odd function. So the graph should be symmetric with respect to the origin. So this graph here is an odd function. Now, then these become, this I would use f theta. F theta is the odd extension of the function y equals to fx. So the odd extension is both piece, this piece and this piece. This is f theta x. This is the expression that we use to define the odd extension. Actually, we talk about this when we study the heat equation and the wave equation on half line, on an unbounded domain, or a half line. Now, if for an odd function, if f theta is odd, and then if we want to find the Fourier series of f theta, then we use this formula. We use this formula, but with f replaced by f theta. Now, if we have f theta here, then this is an odd function. An odd function times an even function is what? Jian Kai, can you hear me, Jian Kai?
Yes.
So when you have an odd function times an even function, so cosine is an even function, right?
Yes.
An odd function times an even function is what?
It's an odd function.
Yeah, it's an odd function. So the product of this is an odd function. Now, an integral of an odd function from negative pi to pi would give you what?
0.
0. That is what we have. This an is 0 here, correct?
Yes.
Now, an integral of an, so this f theta is odd, and sine is also odd. An odd function times an odd function is even. An even function, when you integrate it, it is the double of the integral from 0 to pi is this, right? But you have 2 here.
Yes.
Yeah, and that is how, now in this case, if you look at this formula here, you go back to look at this formula, then you will know that the am terms would be 0, so that you would only have the bm terms, the science terms. That is why when after you have the odd extension, then the full Fourier series becomes just a Fourier science series. Did I make this point clear, Jian Kai?
Yes.
Yeah, Sydney, am I being clear here? Sydney?
So when you use an odd extension, it becomes just a sine series?
Yeah, because the ANs here would become 0. You only have the BNs left. That is the point. Now, on the other hand, if my original function is from 0 to pi, let me use a different color. My 0 to pi. Now, if instead of having an odd extension, I have an even extension. I have even extension that is given by this formula. I have an even extension. Then because in this case, this have an even function times an even function, then I would still get an even function. So therefore, ANs would be, the integral would be from, originally it's from negative pi to pi. So I would now have it from 0 to pi, but I put a 2 here. So it is double of the integral from negative pi. Is double of the integral from 0 to pi. And then in this case, likewise, we have bn or equals to 0. All those Bn are 0, so we don't have the science term. We have only the cosine term. Is that clear? Okay. Now we then have let's look at an example of just to make sure that all of you understand what we are talking about. So I give you a function fx equals to x. And then I ask you to find the Fourier sine series of fx on this interval from 0 to pi. And then also find the Fourier cosine series of the same function on 0 to pi. And then the third question is that I ask you to find the Fourier series of this function from negative pi to pi. Why don't I, instead of me talking, I would just pause for a few minutes, let's say 3 minutes, so that you can read these my computation and then try to understand it. Then I will come back to talk about it a little bit in 3 to 5 minutes. Okay, just trying to work out this by yourself and then look at what I am doing here, trying to see whether you can follow. I may ask some of you to explain, to tell me whether you understand my computation. Okay, try to work on this by yourself first. Okay, so let's continue with this example number 4. So you're given a function, and then you're asked to find a Fourier series, a sine series on the interval from 0 to pi, and then Fourier series, a Fourier cosine series of this same function from 0 to pi, and then a Fourier series of this function from negative pi to pi. Paul, did you read what I wrote there, Paul?
Honestly, I can't see it very well. It's very light.
Oh, that is the problem. So I would probably need to. Does anybody else also have the same problem?
Yeah, it's a little hard to see. Is there any way to
If
zoom in
I
on
make
it
it
on
bigger, can you see? Oh, you can also, if you have difficulty, you can also download the file, the PDF file from the Canvas site, and then it should be more legible. For the PDF file should be easier to read. You can see that. Can you see it now? I make it bigger.
It is definitely easier to read when it's larger, and I can confirm it is much clearer, really clearer in the lecture notes on Canvas.
Right. Yeah. Okay. Yeah, that is okay. Let me just at least make it larger, then you can see it now. I will think about a way to make it darker in here. So we let's look at part 1. We want to write f(x) as a Fourier sine series, so that is Bn sine nx. N runs from 1 to n to infinity. This is just the formula that you use. Okay, this is your fx, and then you just use the formula like this. When you find an integral like this, what is the way that you use to find the integral, Paul? Can you see now, Paul?
Yes. I use integration by parts.
Yeah. This formula is obtained by integration by parts. I skip some detail, but I think you should be able to do it. If or you can just double check my answer. When you double check an integration by part formula, what you need to use actually is the product formula for derivative. You calculate the derivative of this, and then you should get this integrand here. So that is, and then you find the difference from 0 to pi, and that is the integral. So that is how you find Bn. Bn is 2 negative 1 n plus 1 over n. How did I get this negative 1 n? How did this come from? Do you know, Paul?
Yeah, because cosine nx oscillates back and forth between 1 and negative 1.
And then here we plug into when x is 0, okay? When x is 0, this term would be 0, so therefore this would be 0. But when this is pi, then we will get pi cosine n pi. What is cosine n pi? Paul, what is cosine n pi?
Negative 1 to the n.
Yep. When n is even, it is 1. When n is odd, it is negative 1. That is why we have this formula here. So that is how this negative 1 to n plus 1 comes about. Okay. So then we instantly obtain this formula. Sometimes the Fourier series, I did not use the equation side. I use this tutor side because when I use the equation sign, sometimes we make later on we would means point-wise convergent. But here, if we can still use the equation sign, but it must mean only the mean square convergence. So I would, for mean square convergence, I just use the tilde sign, so that would not confuse with what we are about to talk about in the later on. Yoho, do you understand what I'm talking about now? Okay, so he does not have a microphone, I think. So in Paul, did you know that in using Zoom you can also text? I actually never text using Zoom. Can you do that from your end?
Yes, I just did.
Okay, so where did I see the text?
There should be a chat window that you can open.
I showed active speaker window. No, there's a text window. Okay. Anyway, oh yeah, because I share. Oh yeah, I share the screen, so therefore I would. Okay. Yeah. All right. It doesn't matter. Let's continue. Now, for calculating the Fourier cosine series, then we do the computation as before using the formula, using this formula that I keep above here in this in the previous pages. Then we calculate an and a0 and an. Usually we separate the case of when n is 0 and when n is not 0, when n is greater than or equals to 1. And you do the computation again. When the integrand looks like this, you use integration by part, and the result would be this here. So the Fourier series in this case would be this. So this would be a cosine Fourier series. Now, you notice that I have these terms here. The reason is that this term here, when n is odd, what happened? When n is odd, this would be negative 1, negative 1, I would get negative 2, so I would get negative 4 n pi n square. When n is even, this would be 1, this would be negative 1 and 1, so that this would give us 0. So at the end, the summation involves only the odd terms when n is odd. That is why I write as 2n minus 1. When n runs from 1 to infinity, this would run over all the odd terms where these numbers are odd. That is how this comes about. Any question? Now, we now calculate the full Fourier series. In this case, fx is a0 half and n from 1 to infinity an cosine nx plus vn sine nx. And then the ANs and the BNs are given by these formulas. AN is given by this formula here. Now, cosine is an even function, x is the odd function, so the multiplication of odd function and an even function, as Jian Kai just said, is an odd function, so therefore the integral from negative pi to pi is 0. They cancel out. And for an odd function, the area here and here cancel out, so that therefore the integral is 0. And the Bn, so this is from negative pi to pi. The Bn's now, because this term here is odd times odd, you get an even function. Therefore, the integral from negative pi to pi is 2 times the integral from 0 to pi. And so therefore, we have this equals to you can do the computation as what we did before, and you get this. Now, if you compare what we do here, this formula, and the Fourier science formula is exactly the same formula. So that those two are exactly the same formula. And that is actually consistent with what I just said previously, that the full Fourier series is a generalization of the case of Fourier sine series and Fourier cosine series. If this function is odd on this interval, when you expand it as a Fourier series, you should expect that it have only the science term, because odd function expressed as a sum of odd function. If f is even function, then when you express it as a full Fourier series, then on the right hand side, you should expect that this involve only, instead of sine, you should involve only cosine function, because cosine function is an even function on this interval. So that is the idea about this. Any other questions? Let me see. Okay, why don't we have a few minutes break, and then we will meet again at 7:15. Okay, we have about 7 minutes break. We'll meet again at 7:15, and then we will cover the rest of the material in this section. Okay.
Sounds good.
excuse me. Okay, so everybody's coming back. Let me see what did I do wrong. Paul, you can also see my share screen now, right?
Yes, I can.
Okay, good. So we can continue with the class. All right. So here, we're trying to do is that if you look at this formula that we have here, this we have x has a Fourier series. This fx equals to x. It has a Fourier series expansion as a Fourier sine series. Now the so this is the formula that we have here. This is the formula that we have here. On the left-hand side is x. Of course, x is not a periodic function, but on the right-hand side, all the sine functions are periodic functions and have period 2 pi. So you cannot expect that the left-hand side would equal to the right-hand side from negative infinity to positive infinity. Now we have it could equal to the left-hand side. This would be equality from negative pi to pi. Now, so in order to extend a function that that is true from negative pi to negative infinity to positive infinity, we would take only a part of this function fx equals to x, which the graph is this, and we extend it as a periodic function. So that is what we call as a periodic extension of the function. The function originally is defined from negative pi to pi, and we want to extend it to a 2 pi periodic function. So there's a periodic function with period 2 pi. How do we do that? We just move the graph to the right or to the left of 2 pi unit each time. Then we get a periodic function. The graph looks like what we have here. That is the graph. So then we start with a function that is defined from negative pi to pi, and then we can extend this function to a function that is a periodic function with period 2 pi, and then analytically the expression for this periodic extension, which we call as f theta, is given by this formula, but graphically it is just this graph here. It is just this graph here. That is graphically, and then analytically that is the expression. So if you remember that it's just that you move the graph by an integer times 2 pi unit, either to the left or to the right, depends on whether k is negative or k is positive in this case. So that in the picture, fx is this function here, and the periodic extension that we just move the graph to the right or to the left by 2 pi units. That is a periodic extension. Does this make sense? Paul, did you follow what I was trying to talk about?
Yes, I think so.
Okay. All right. Now it's only after we talk, we have this extension, periodic extension, that we can talk. We now come back to talk about the point-wise convergence of the Fourier series. I have this function x can be expressed as this Fourier series. Now I told you that this Fourier series would converge in the mean square norm, but I also mentioned that mean square norm convergence does not implies point-wise convergence. And now in this theorem, in fact, when Fourier first invented this Fourier series, he was not careful enough about this convergence. And it's Dirichlet who first proved that under some condition, this Fourier series converges point-wise. Now, okay. So a function is defined first from negative pi to pi, but we extend it to from negative infinity to positive infinity as a periodic function, as a periodic function with periods 2 pi. And this function is continuous except finitely many points. So it could have some, it's what we call as piecewise discontinuity. So it could have jump discontinuity at some points. And its derivative, it is bounded, derivative is bounded, and it exists except at finitely many points, and it's called, is continuous except at finitely many points as well. So this is what we refer as a piecewise smooth function.
Professor? Professor Fu?
Yes?
Are you writing on your screen? I can't see anything.
Oh, you cannot see my screen now?
No, it just stopped at you underlining periodic extension and pointwise convergence. I can't see. Did you write anything after that?
Yeah, I wrote something piecewise smooth. Can you see piecewise smooth?
No, am I the only one having this issue?
I don't see it either.
I don't see anything either.
Okay, all right. Let me stop sharing and then share it again. All these new technologies. All right, let me. Okay, I hope you can see it now. Can you?
Yes.
Marisa, you can see it now, right? Okay, good.
Yes, thank you.
I can as well. Thank you.
All right. So what I was trying to say is that we now we have discussed the mean square conversion. We want to discuss point-wise conversion. So it will not be point-wise conversion for every function, but we need to set up the conditions under which we will have point-wise conversion. So the conditions are the function is what we call as piecewise smooth. What it means is that it could you can decompose it into is a function like this function here. You can decompose it into small pieces, and each piece is smooth. Smooth means that the function is continuous, and then its derivative is also continuous. But here we could have the situation where we have small pieces. The function is defined in small pieces, in pieces on which it is all smooth. So that is what we mean by piecewise smooth. Now, for piecewise smooth function, then we can talk about the convergence of the Fourier series. So when we say about convergence of a Fourier series, there's an infinite series. Then when we talk about convergence, what does it mean? It means that the finite sum, this is a finite sum. This is a sum, we sum it from 1 to n. This is finite sum. The finite sum converges. Now, the thing is that it would not converge to original function. It will converge to 1/2 of f plus at plus and 1/2 plus f at minus x. I would now explain this here. Now, f plus is just the right-hand limit of f as this t approaches to x plus, and f minus here is just the left-hand limit as t approaches x from left. Like if this point is x here, what would be f? Let me say this number is one. This number is say 2. Okay, the scale is not good. Then Sydney, what would be f? Let me call this point as pi half. Okay, pi half. So what would be f plus pi half, Sydney, in this notation?
I'm sorry, what was the question?
The question in this picture in this picture here, what would be f plus pi half? F plus is the right-hand limit as t approaches x from the right. Yohei, do you know the answer, Yohei? George. Okay. All right. Sydney, did you find the answer? It's 2, right? As x approaches t, as t approaches this pi half from the right, the right-hand limit is going to be 2.
Oh, okay, yeah. I was still reading. Sorry.
Okay. So f negative pi half would be what?
1.
1. So the answer. So this would mean that the Fourier series will converge to 1/2 of 2 plus 1. So that is a 3/2. That is the middle of these 2 points. So that is what this point-wise convergence tells us. Like in this case, it will converge to this point here in the middle. All right.
Quick question.
Yep.
So I'm guessing that none of our problems or examples will include sort of a graphs or pictures like this. And I'm curious how it is that was this just a particular example, just irrespective of the rest of.
Okay, I see your points, and then I would come back. We would have an example to illustrate these things.
Okay.
On. Okay, maybe
Just
we can.
notational. I understand.
Okay.
Thank you. I appreciate it.
Yep. Okay. So this deletion theorem, the proof was not provided. Actually, the textbook give a slightly different version of this deletion theorem, and I'm not going to prove this theorem for you, but you can if you want to really know the proof, you can look at the book by W.T. Corner. Is a very nice book published by Cambridge University. It's called Fourier Analysis. You can find the proof from there. Okay. Now, coming back to the example that we have, we know that the Fourier series for x on negative pi to pi is given by this formula. We did the computation, correct? Deanna, you have been very quiet. Are you still there, Deanna?
Yeah, I'm still here, Professor.
Yeah, okay. So we talk about this convergence. Then this Fourier series is this. Now we're trying to apply the Dirichlet theorem. Let me come back to the Dirichlet theorem. If the function is continuous at the point x, then the left limit and the right limit will be the same. Both of these would be the same as fx. So 1/2 of this would be we give you fx. So at the point of continuity, the Fourier series converges pointwise to the value of the function. It is only at this jump discontinuity that we need to average the value in order to find the limit of the Fourier series, the sum of the Fourier series. Now, we come back to this example. Now, the function fx is, this is the graph of the function fx. So, okay, the function, of course, is continuous after the periodic extension is all continue on these points from negative pi to pi, but that's not including the endpoints. So the convergence would be from negative pi to pi. However, when x are those endpoints, like at pi, you look at this, you would have a jump discontinuity from pi when you approach pi from the left. So f negative pi would be what? Let me ask Melissa, what would be f negative pi? Here, actually, the negative pi means the not f and negative pi, but the limit from negative pi. So this notation is a little bit probably, let me change the notation a little bit. It's not good note. So f negative this pi maybe is a little bit better, but that means that you x approaches pi from the left, then the limit would be what, Marisa, in this graph?
Is it just approaching pi?
Yeah, that is pi. And if f approaches pi from the right, what would be the limit then?
Would it be the negative pi?
Yeah, and then if you average these two, what you get?
0.
0. That is why you get the 0 here. Of course, you can actually see that this limit of this must be 0. The sum of this must be 0 when x equals to pi, because if you plug x equals to pi into this identity, what you have here is all zeros, right? You add up a bunch of 0. Am I right? So therefore, that is, in this case, you get the 0. Now, if you look at the Fourier series of the cosine function, so I mean of x, this is x extended as a Fourier series from 0 to pi. From 0 to pi, a Fourier cosine series, if we're going to find a Fourier cosine series, we have to extend it to an even function. So therefore, the graph of this function is this. So it actually is all continuous. So at x equals to pi, this would equal to pi. When x equals to 0, this would equal to 0. That, now, if I plug x equals to 0 into this formula, cosine of 0 is always 1. Cosine of 0 is always 1. So I would get, from here, I would get 1/2 minus 4 pi. This would be all odd terms, so 1 over 1 square, 1 plus 1 over 3 square, all those. And then this equals to 0. Then I move this 1/2 to the right-hand side, and I modify both side by pi and divide both side by 4 pi. Then we get this nice formula that when you add all the terms square of reciprocal of all integers, odd integers, the sum is actually pi over 8. We can also get this formula from Basel's, from Pascal's equality, but that is what we have here. Any questions? Emmett, you're very quiet. Do you have any question, Emmett?
No, sir, I'm good for now.
Okay, you're okay?
Yes, sir.
Okay. All right, so that is, now let's summarize what we have here, what we have done. If you are given a function fx on 0 to pi, then we have two ways to extend it. Either extend it to an odd function. If you extend it to an odd function on from negative pi to pi, if you extend it to an odd function, then what you get is going to be a Fourier sine or cosine series. GLR, what would you get? Can you hear me, GLR, Mr. Zhu? So you will get a Fourier science function, science series. And if you extend it to an even function from negative pi to pi, then you get Fourier cosine. Now, if you are given a function fx on negative pi to pi, if it is neither even or odd, then you would have full Fourier series that involve both sine and cosine. So that is, and then the formula are given in the previous pages. Now, what we are going to do next is to find the Fourier series on an interval, not necessarily from negative pi to pi, but from any negative L to L. So we generalize this from negative pi to pi. So again, in this case, we extend it to a periodic function with period 2L. So L minus negative L is 2L. So that is a periodic extension, but here is from negative L to L. And you just move, in this case, you move the graph, to the right or to the left, 2L unit at a time. And now, so the idea, there are actually two ideas. You can go through the kind of thing that we did before, but another idea is to convert this function that it has a 2L period to a function that has 2 pi periods. So convert this have 2L period and to a function we will call f hat x as with 2 pi periodic function. Now, how did we do it? This actually in a new function we will use t. So how do we do that? You just need to use a substitution here. So the x is equals to LT pi. So here when t equals to pi, then x would equal to L. So then this function becomes a function with a period 2 pi. I mean, how do you check whether a function with a period 2 pi? You just add t by 2 pi, and then you should get ft back, f hat t back. So that is, you just use this formula, you replace the t here by t plus 2 pi, this modifying this, you get L over pi times t, and then this pi and this pi would cancel, you get 2L. But because this function has 2L as the period, so then you will get f hat t. So that is how, that is why this function here is a function with a period 2 pi. Now, so then, because ft is a 2 pi periodic function, so we have a Fourier series expansion like this. It's just as before, but just have the x replaced by t, because this is a 2 pi periodic function. Now, the ANs are given by the formula as before. This is the formula that we had before. Now, I want to substitute back, use this substitution. If so, remember, x equals to L pi over t. So therefore, t equals to pi over L times x. So I just use this substitution here. Then I get this formula. Now, when you do a substitution, remember, you also need to change the lower limit and the upper limit. When t equals to pi, x equals to L. When t equals to negative pi, x equals to negative L. That is why you have this formula to calculate the Fourier series. Now, likewise, the b n are calculated by this formula using our old formula, but with a substitution. So just in summary, when you have a 2L periodic function, the So now you replace the t here, the t by t is pi lx. So the t here is pi over lx. So then you get this this formula here becomes this formula here becomes this formula. So that is become this formula. So the so then we now for any function from negative L to L, define a function from negative L to L, we can find a Fourier series in this way, in this form. And this AN and BN are given by these two formulas. AN and BN are given by these two formulas. And the theorem, the Dirichlet theorem for this is exactly the same. At the jump discontinuous points, you just find the average between this jump, and for discontinuous points, and then it's just the point-wise convergence is to the value of the function. So that is the Dirichlet theorem. Okay, let me just pause a little bit and let you digest what I was talking about. Tom, did you follow what I'm talking about, Tom?
I think so.
Okay. Austin, are you still doing okay, Austin?
Yeah, I think so for the most part.
All right. Okay. So that's fine. All right. So we now look at the example again. So L is a given number. We still have our function fx equals to x, but we are now going to extend it from as a Fourier science function, but on the interval from 0 to L. When L is pi, we already done it, and now you would have then you also extend it as a Fourier cosine series from 0 to L, and also the full Fourier series from negative L to L. Now, there are actually two ways to solve this problem. One way is that you just plug into the formula. This is the formula for Bn. Why do we have this formula here? Original formula was that Bn equals to 1 over L from negative L to L x sine n pi xl. When L is pi, that is the formula we had before, but for general L, this is a formula. These two formula are the same. Jiankai, can you explain why these two formula are the same? Jiankai?
Let me see. Because it is because they are even, and this one is 0 from L and another is negative L to L, so it's double the size. I mean, how to say?
Very good. Excellent. That is exactly what it is. Everybody understand? If you didn't understand, then you. Okay, so then for the Fourier science series is given by this formula. That is given by this formula. All right. Now, this you can also find this series by using substitution. So that is the formula we put when it is from negative when it's from 0 to pi. That we put in the previous example, but I just change the variable. Instead of having x, I change it to t, but t now runs from 0 to pi. Then I do this substitution, t equals to pi over L times x, so that when x is L, x equals to L corresponding to t equals to pi. Then I substitute this into here, then that is what I get. That is the formula. Just the t here is pi x, and then this t is here. Now, then I multiply both sides by the reciprocal of this term. So then I would have this formula. So this would be L over pi. That is how these terms comes about. So that is another method. Let me summarize. When you're trying to calculate the Fourier series from negative L to L, you can either use this kind of formula directly do the computation, or you can convert it by a substitution, convert it to a problem that is from negative pi to pi, and then find the Fourier series via substitution. So this is the method of substitution. All right, and then the cosine series is also similar. And then the full Fourier series is the same as the sine series because, as Jiankai just explained, when you calculate this coefficient, it would be double like this, and then when you calculate an, it would go 0 because the function f equals to x is odd. So the full Fourier series, when you expand it out, it would involve only the sine function. It would not involve the cosine function. Okay, so this is actually the end of this section. But let me just give an example of one further example. Example 6. Say now, the bad thing about this. Let's look at this. This series here. The bad thing about this Fourier series is that it's an infinite series. So the sum sometimes is not easy to find. Now this of course is a simple case, but you can, if you want to find an approximation of x, you can just find the finitely many terms. So let's say I would use n here. Run from only 1 to 3, then this, although you will not be able to, this is not exactly equal, but it actually, as you let this number larger and larger, this actually is going to be a better and better approximation. So that is the case when you run when you have the approximation. So this would let me let L equals to pi in this case. Then this would be n equals to 1. This would be positive. So this would be 2 sine x, and then the next term would be negative 2 over 2 sine 2x, and this would be a plus 2 over 3 sine 3x. So this is a finite Fourier series is an approximation. This is only an approximation. That the right-hand side is an approximation to the left-hand side that holds from negative pi to pi. Now this actually does not sound like a big deal. X is a function that is just quite simple. Then you express as a trig function. However, Fourier analysis actually is a very, very useful tool in a lot of science. The reason is that sometimes when this function is very complicated, like you have the exponential function and then the several exponential function combined together, or have some function actually you can even write it explicitly. Then using the Fourier series to express it, it actually is a very very useful tool, and it is also very useful tool in signal processing, because you want to store a function fx. If I give you an arbitrary function, you want to store the information of this function into a computer, let's say. I mean, but the function is a real value, has infinitely many value, and it's actually uncountably many value, and the variable is also uncountable. So the idea is that, okay, you can extend this as a Fourier series. This is a finite Fourier series, and an cos, and I will call nx plus bn sin nx. Now, then you can store the information about fx here can be stored with these Fourier coefficients, A1, B1, and AN, BN. So this information is enough to characterize this function fx. That is why it is important in signal processing. Albert, you actually was learning something kind of to this kind of similar to this, right? You mentioned to me, Albert, that you want to store the information of a function using finite value, and that is it. That is one way to do it. I would also mention an application, actually, is something I actually quite interested in music theory. So you all know that when you play say a violin, and when you play a piano, or when you play a trumpet and clarinet, they all sound different. But how did why different instruments sound different? Emmett, do you know the answer to this question? Why did how instruments sound differently? Did I lost my voice here? Nobody's answer.
I can hear you.
You cannot hear me?
I can hear you.
You cannot, or you can. Can you?
I can, as in the can, the song.
Okay. All right.
Loud and clear.
Okay. Emmett, are you still there, Emmett?
Yes, sir, I'm here.
Okay. So I was asking you, you told me you play music instrument. How do you explain that different music instrument sound differently?
What was the question again? I'm sorry. How do I
So
explain?
you play a clarinet and you play a trumpet, they sound differently.
It's because they have different frequency.
Okay. It comes from Fourier analysis. A clarinet would have the sound curve. It depends on the sound curve. The sound curve of clarinet looks like this. For violin, I forgot exactly how it looks like. The sound curves would look like this. Now, when you extend these function, these are periodic function, so therefore it can extend using a Fourier series. So the quality of the sound usually in music theory is called timbre. I believe timbre of the sound is actually depends on when you extend this function, this wave function or sound curve as a Fourier series. Those are periodic functions. You can express it as a Fourier series. It depends on the relationship between those Fourier coefficients. So two instruments sound differently because when you express their sound curve as a Fourier series, the relationship, those Fourier coefficients are different. That is a scientific explanation of why different music instruments sound differently. Okay.
Cool.
Okay, so I would now just stop here, but and let you go back to review this section. But let me just briefly review what we are going to, what is going to be covered in the in test 2. So test 2 is going to cover a section I said is 2.3 to 2.7 and 3.1 to 3.3 is going to cover this section. And the homework will be due on I think for these sections, or we already have one. Or I would return the grades and return your homework to you tonight, later tonight. And we have a new homework due on from 2.7, 3.1 to 3.3 due on Wednesday. But I'm thinking, let me ask all of you: do you prefer to have our second test next Monday or a week after next Monday? Sydney, do you want to have it? Is it we can do it. I can postpone it for 1 week so that you have more time to prepare. Anybody would need more time to prepare for the test, or you think you are okay?
I think next Monday is fine.
Okay, next Monday is fine. Then we will go ahead with next Monday. Okay, so that will be next Monday, and the review I'm going to. I mean, there's nothing to review. What you need to do is exactly as what you should prepare, what you did when you prepare for the first test. That is to, I'm going to post the solution, study the solution to the homework. So we have only 2 homework assignments after the first test. So study the solution to homework. I think that's homework number 4 and 5. I will post the solution on this Canvas site, and now for the test, you should, because it's an open book test, that means that you are allowed to read it, whatever. But I do warn you that you should not Google or search internet or it should be done with, independently and without any internet resources, without web resources. I doubt that you would find any help from this test or by Googling it anyway. But it's always good for you probably to have to study the solution beforehand. And any question regarding the test?
Well, we know our grade for the homework this Wednesday, that's due this Wednesday before the test.
So Wednesday, after midnight is due. I would, so this time I would not accept any late homework, okay? In fairness to all of you, I would not accept any late. You need to hand it in before midnight, no matter what you do, just hand it in. Then I will return the homework to you on Thursday and post the solution on Thursday. Is that okay, Sydney?
Yeah, that's fine.
Okay, good. Any other question? Homework number 5 will be returned to you.
I have a question, Professor. Is this next exam going to be the similar format to our first exam? Will you give us about like 7 questions and we have to choose 5 from them?
Exactly. So
Okay.
we'll return homework return on Thursday. Okay, and then exam we are going to have. I haven't made up the exam yet. I would say that we have test 2 would be similar to in format to test 1. So we will have around 7 problems, and I will ask you to solve 5 of them. Okay.
Quick question.
Yep.
So the current homework, right, is the 3.3 up to 3.3.
No,
right.
The current homework is 2.7, 3.1, and this is homework for number 5. Homework for number 4 is or you already should have turned in.
Right. Okay. So then I understand a number of people in the chat have said that they were cool with the test being next Monday. I'm just wondering if, I mean, for me, having a weekend schedule, generally with my job, it would be helpful to be able to get the homework back a little earlier. The current homework, anyway, the latest homework, if it's what's is going to be exam material. So I guess would it be possible to take a vote for next Monday versus 1 additional week for the exam? Not to rehash an already done thing, but throwing that out there.
Yeah. Okay. I'm open to it, but of course, I have already write this down as part of the remote instruction. If you go back to look at the remote, I did mention that our second test is going to be on April 13th. So
yes, and I see that too. It's not a surprise. Just that we were given the option.
Yeah, but I do understand your point that if some of you may need more time.
Okay, but ultimately, if next Monday is what we're doing, next Monday is next Monday that'll be what we're doing.
Okay. Yep. And then I Austin, I think you should be able to do fine, but then this week that just means that this weekend you probably need to.
Right, I've got my focus. Thank you.
Focus on this thing, and then all right. Any other questions?
Yes. So we have class in the first half, and then you'll release the test as a file during.
I will release the I guess what is the best way to release? Okay. I would put it as a file on the Canvas side, and I think you should be able to download it or look at it from your cell phone, and you can do the problems on a piece of paper. I want you to do a problem so that each problem is only one page, have only one problem, and then after that, you just scan, use your cell phone to scan this as a PDF file. Then you upload it as a quiz. I would assign this as quiz. Then you can upload it as a quiz to the Canvas side. Is that clear, Sydney?
Yes. Also, another question is that while we take the test, are we supposed to be in conference or on Zoom while we take it? Or
okay, you should be on Zoom, and I would actually prefer all of you to turn on your Zoom video. But I understand some of you may not have a video. If you don't have a video, then that is also fine. Okay, I would not force you to do that, but I would prefer. Let me just say that if you have a Zoom video, just turn it on. Okay.
And the test will be from 7:30 to 10:30?
Yeah, you can turn it in earlier, but it's the time limit is going to be the test. I mean, as you know from the first test, 1.5 hours should be enough. But here I will give you 3 hours, so then you can have extra time if you want. Is that okay, Melissa?
Yeah, and if we're not able to use our webcam, is that going to be an issue?
No, I'm okay.
Okay.
Yeah, it has been very difficult time, not just for you, but also for me as well. But I'm determined to accommodate and then trying to help you guys learn as much as you could.
Thank you very much.
Okay. Any other questions? Okay, so if not, that we will just end the class today. But do try to come to the office hour on Wednesday, so I can go over some of the homework problems. If you have question with the homework problem is going to be from 11:15 to 12:15 on Wednesday, and on next Monday, the same time, if you after you review it, the test, and then you still have question, then I would also have office hour next Monday on the same time. Is that clear? Okay. Okay, so I will see you either on Wednesday or next Monday then. All right. Okay. Good night, everybody.
Thanks.
Thank you. Have a good night.
Oh, before you guys go, let me ask you opinion. Do you think this format using Zoom is better, or the old format using Canvas just play a video is better? Austin.
I think this is better. I think.
I really like this.
Okay.
I also really like the potential for sort of having the lecture notes uploaded, because then I can sort of take down, copy all of those notes, and then I'll have that. And then as we're going over it, there's no trying to write to do the note taking while also sort of paying attention to sort of our lecture. So I feel like going forward, this will be a very I think it'll be a great format.
Okay, very good, very good. So then we will keep it this way, that we will instead of just give you a video and play the video, some of you get bored, and I will just give you a live lecture, but give you the lecture notes ahead of the time. Okay?
Sounds good.
Okay, good night, everybody. Bye.
Thank you.
Good night. Thank you.